Hi, thanks for joining me. Today we're going to be going over a step 2 problem from the 2020 paper. So step is the entrance exam you have to do if you want to study maths at Cambridge, and I've already made a few step videos. I'll leave a link in the description below to a playlist where I've solved a bunch of step problems as well. Anyway, this problem involves my favourite function, or one of my favourite functions certainly, the digit sum function. So let me read out the problem, I'll give you guys a chance to have a go at the problem, and then I'll go over a solution. Okay, so as I said, this problem here considers the digit sum function, which in this problem we're denoting d of x, and it basically just sums the digits of a positive integer when you write that positive integer out base 10. So for example, d of 249 is just 2 plus 4 plus 9, which is 15. Okay, so part 1 of this problem is we want to prove that x minus d of x is always at least 0, so it's non-negative, and that 9 divides x minus d of x. So x minus d of x is a multiple of 9. Part 2, we want to prove that 9 divides x minus 44 d of x if and only if 9 divides x. So in other words, x minus 44 d of x is a multiple of 9 if and only if x is a multiple of 9. Okay, and now what we're going to do is sort of a second part of part 2, is we're going to suppose we have some x for which x equals 44 d of x. Then we want to show that if x has n digits, we want to show that x must be at most 396 times n. And we also want to show that x must be at least 10 to the n minus 1. And from that we want to deduce that n is at most 4. And then what we want to do is find some x satisfying x equals 44 d of x, and then show that that x value is unique. So the last part of that, we want to find some positive integer x for which x equals 44 d of x, and then we want to show that that's the only possible value of x which has that property. Okay, part I, the final part of the problem is we want to find the unique solution to x equals, now this guy here is 107 d of d of x, so the digit sum of the digit sum of x. And we want to show that that is a unique solution to this equation here. Okay, so a lot of different parts to this problem here, getting more and more difficult as you go down. But if you want to have a go at this problem, pause the video now and give it a go for yourself. And I'm going to jump straight into a solution. Okay, so before we get into the solution to part 1, let's introduce some sort of notation. We're going to write x, which is some arbitrary positive integer, which we'll suppose has n digits, so it's an n digit long positive integer. And we're going to write it as the sum from r equals 0 to n minus 1 of ar times 10 to the r. So here ar are just some digits from 0 to 9, and an minus 1 is non-zero. And so this is essentially just saying that x is an n digit number. So for example, if x was 427, so if x was 427, then that would mean that n is 3. And then basically what this is writing it as is this is 4 times 10 squared plus 2 times 10 to the 1 plus 7 times 10 to the 0. So this would be our a2, this would be our a1, and this would be our a0. So that's just giving you an example of how we're going to be writing x like so. So let's show that x minus d of x is non-negative for any arbitrary positive x. So this was just the case x equals 427. So we want to show that it's not negative. Well, let's just do x minus d of x like so. So x minus d of x is just, well, if you write x like so, it's the sum from r equals 0 to n minus 1 of ar times 10 to the r. And the digit sum of x is just the sum of the digits in x, but the digits in x are just these ar's here. So we're subtracting off the sum from r equals 0 to n minus 1 of ar, like so. Or we can bring these two summations together and get that this is equal to the sum from r equals 0 to n minus 1 of ar times 10 to the r minus 1, like so, by factoring out the ar. And we can clearly see that this is non-negative because each of the ar's are non-negative, and 10 to the r minus 1 is always non-negative. So yeah, this guy here is always going to be non-negative. The next thing we want to do is show that 9 is a factor of this guy here, so x minus d of x. So we can actually use this expression here. We want to show that this guy here is a multiple of 9, and the way we're going to show that is by showing that 10 to the r minus 1 is always a multiple of 9, and perhaps the easiest way to do that is noticing that 10 to the r minus 1 is the same as, if we kind of factor this, 10 minus 1 times 1 plus 10 squared plus so on, all the way up to 10 to the r minus 1, like so. And you can just verify this by expanding this guy out. This is kind of like, or if you were to divide both sides by 10 minus 1, you get the sum of a geometric series. But yeah, 10 minus 1 we know is 9, so we can write 10 to the r minus 1 as 9 times something, and hence 10 to the r minus 1 is a multiple of 9, and that solves part 1. Let me clean the whiteboard and we'll move on to part 2. Okay, so for the first part of part 2, we want to show that 9 is a factor of x minus 44 d of x if and only if 9 is a factor of x. So x is a multiple of 9 if and only if x minus 44 d of x is a multiple of 9. Okay, so the way we're going to do this is just start from the left hand side here, x minus 44 d of x. And what we're going to do is a little trick by adding and subtracting the same thing. So what we're going to do is add and subtract 43x to both sides. So if we add 43x and then subtract 43x, we can write this as 44x minus 44d of x minus 43x. Okay, because all we've done is added on 43x and then taken it off again. But then this first bit here, we can just factor out of 44 and write this as 44 x minus d of x, and then minus 43 of x, like so. Okay, and now hopefully it's quite clear. We're going to use the result from part 1 that x minus d of x is always a multiple of 9, and kind of look at both sides mod 9. If you don't know what modular arithmetic is, don't worry too much. But essentially what we're going to do is notice that this guy here is always a multiple of 9. And hence for this guy here to be a multiple of 9, that's going to clearly be true if and only if this guy here is a multiple of 9. So essentially if we look at this mod 9, we get that x minus 44d of x is therefore congruent to minus 43 of x mod 9. Okay, because this guy here is always a multiple of 9, and obviously we're multiplying it by 44, so that doesn't change anything. So we get that x minus 44d of x is congruent to minus 43 of x mod 9. But now notice that the key thing here is 43 and 9 are co-prime. They share no common factors, and hence this guy here on the right hand side is a multiple of 9 if and only if x is a multiple of 9. Another way of thinking about that is 43 is a prime number. So if you wanted this right hand side here to be a multiple of 9, well 9 is just 3 squared, but 43 has no factor of 3. So the only way we can kind of get this right hand side to be a multiple of 9 is if that property of being a multiple of 9 comes from this x here, because you're not going to get anything from this 43. So this right hand side is a multiple of 9 if and only if x is a multiple of 9, and thus x minus 44d of x is a multiple of 9 if and only if this right hand side is 0 mod 9, which is true if and only if x is a multiple of 9, and we get our conclusion here. So x minus 44d of x is a multiple of 9 if and only if x is a multiple of 9. Now let's continue with the rest of part 2. Okay, so now we want to find a solution to x equals 44 times d of x and show that that solution is unique. Now this is a very classic step style where the problem itself is very difficult. Just look at, if we were just given this guy here, it would be very difficult. But the way we're supposed to solve it as mathematicians is to use our earlier parts, the things that we've already solved, to our advantage. Okay, so in the first part of part 2, we showed that x minus 44d of x is a multiple of 9 if and only if x is a multiple of 9. So if we're saying that x equals 44d of x, then that just means that x minus 44d of x is 0, which is certainly a multiple of 9. So that tells us that x must be a multiple of 9 in this case. So for this to be true, then we must have that x is a multiple of 9. So we can write that as 9 divides x, like so. Okay, but also if x equals 44d of x, then it's very clearly a multiple of 44. So we also get that 44 must divide x as well. Now 44 is just 2 squared times 11, and 9 is just 3 squared. So 9 and 44 share no prime factors, they are co-prime, which means we can combine these two pieces of information together to give us the since we know x is a multiple of 44 and x is a multiple of 9, we can combine those together, noting that 44 and 9 are co-prime, to then tell us that x must be a multiple of 9 times 44. Okay, so whatever this guy is here, it must be a factor of x, but 9 times 44 is just 396. So we must have 396 is a factor of x. Now, from the thing that we just proved, we showed that x must be at most 396n, but we also showed that n must be at most 4 for this guy here to be true. So that means that certainly x is less than or equal to 396 times 4. Okay, just combining this guy and this guy together. So x is less than or equal to 396, 4, and we know that x is a multiple of 396. So that just tells us that we only need to check a few cases. X equals 396k, and that's for k being in the interval 1, 2, 3, 4. Okay, because we know for any k bigger than that, we're going to get that x is, we're going to contradict this inequality here, because x would then be bigger than 396 times 5, which is not possible. So we have that x equals 396k for k equals 1, 2, 3, 4. So now we've just narrowed it down to 4 different cases, and we have to check each one. So you just check each of these 4 cases. These are the only 4 candidates, and you'll see that k equals 2 is the only one that works, and that proves uniqueness. But let me just show what k equals 2 is. If we just plug it in, if we let x equal, we'll call it x2 to denote it's the case k equals 2, is just 396 times 2, which is just 792. Okay, 792, if we work out its digit sum, d of x is just 7 plus 9 plus 2. 7 plus 9 is 16, plus 2 is 18. Okay, and you can verify for yourself that indeed x2, 792, is indeed 44 times 18 by just doing your favourite method of multiplication or division, whichever you prefer. Anyway, that's how we do part 2, and also, yeah, for this problem you'd have to show that k equals 1, 3 and 4 aren't solutions, but yeah, k equals 2 is the only solution from this logic, and we have to check that it works, and thus the solution is unique. Now let's move on to the final part of the problem, part 3. Okay, so now we move on to the final part of the problem, part 3, sort of the grand finale, the thing that the whole problem has been leading up to, and this part will separate the good students from the excellent students. So what have we got in store? We want to find a positive integer x for which x equals 107 times, x equals 107 times the digit sum of the digit sum of x, and then once we've done that, we want to show that it's unique. So what we're going to do is follow the exact same recipe we've been doing for part 1 and part 2. Show that x minus 107 d of, we want to firstly show that x is a multiple of 9 given this thing here, and then after that we want to build some upper and lower bounds on x, and thus an upper bound on n like we did in part 2, and then from that we'll only have some cases to test, and then from that we'll show that only one of those cases actually works, and hence we'll find a solution, and that solution will also be unique. So firstly, to show that this guy here is a multiple of 9, we're going to do a similar thing to what we did back in part 1, where we're going to subtract off something and add on something. So we want to show that x is a multiple of 9. Well, firstly note that 0 is just equal to x minus 107 d of x, like so, just by bringing the 107 d of x to the one side. Okay, and now what we're going to do is add and subtract something. So firstly, we're going to add and subtract 106x. So I'm just going to write that on here. So if I write 107x there, and then subtract off 106x here. But what we can't do is we can't just factor out 107 and say that x minus d of x is a multiple of 9, because we don't know that. What we can do though is use a very sort of slide trick and add and subtract on another something. So we're going to add and subtract 107 just d of x now, and then add it on again. And then subtract this guy here, and then the minus 106x there. Okay, and the reason we're doing that is now we can kind of factor. We can write this as 107 times x minus d of x. And now we know that this guy here is a multiple of 9 from part 1. Okay, and then add on 107 times d of x now minus d of x. Now we also know that this guy here is a multiple of 9 just by using the result from part 1, except replacing x with d of x. So if we call this, say, a instead, we're doing a minus d of a here, and that is a multiple of 9. And then of course we've got the subtract 106x here. Okay, so we've got 0, which we know is a multiple of 9, is equal to 107 times this guy here. This is a multiple of 9. This is a multiple of 9. So all of this here is a multiple of 9. So for the left-hand side to both be true, we need minus 106x to be a multiple of 9. And again, 106 and 9 share no common factors. They're both co-prime. And hence, for this guy here to be a multiple of 9, which we know it is, we need the multiple of 9 to kind of come from somewhere. And it's not going to come from this 106 because it has no factors of 3. It's not a multiple of 3. And hence all of the sort of 9-ness of this number, the the only way this thing here is going to be a multiple of 9 is if x is a multiple of 9. So then from this logic here, we get that x is a multiple of 9. So it's a bit of work and a few tricks, but we get that x is a multiple of 9. But we also know that from this guy here, x is clearly a multiple of 107. Okay, and because it's 107 times something, and this guy here is an integer, a positive integer. Okay, so x is a multiple of 9, but it's also a multiple of 107. Now again, 107 and 9 share no common factors, because 107 is not a multiple of 3. And so that means that x is a multiple of 107, x is a multiple of 9, and because 9 and 107 are co-prime, we can combine those two facts together to tell us that 9 times 107 is a factor of x. Okay, and 9 times 107 is just 963. Okay, so x is just x is a multiple of 963, which tells us that x is equal to 963k for some k. Now what we want to do is find an upper bound for k, like we did in part 2, and then we'll just have some cases to test. Okay, so for the final part of the problem, we are going to find some upper bounds and lower bounds to x in terms of n, where n is the number of digits in x, and then from that find an upper bound for n, and then we'll just have some cases to test, as I said. Okay, so first we have that x is equal to 107 times the digit sum of the digit sum of x. Now, firstly, notice that this thing here, d of x, is some number, and from part 1, we know that d of x is less than x. So if x is an n-digit number, then d of x is going to have at most n digits. Okay, so this number here, which is in the brackets, the d of x, is some number with at most n digits. So then we know that when we take the digit sum of this number here, which has at most n digits, we know that that is at most 9 times n, because each digit could be at most n, and then this guy in total is just at most 9 times n. So if we combine this together, we get that x is less than or equal to 107 times 9n, which is just 963n. Okay, so let me quickly go over that. The digit sum of x, well, we know that that is less than or equal to whatever x is. Okay, so that means if x has n digits, then certainly d of x will have at most n digits. It could have fewer, but it has at most n. It probably will have fewer if x is large, but it will certainly have, it won't have any more. Okay, and then because it's a digit with a number with at most n digits, when we take its digit sum again, so this d here on the outside, we're going to get at most 9 times n, because each digit could be at most 9 and no bigger. Okay, and that's where we get this 9 in from, and then we're just multiplying by 107 to give us the 963n there. So x is at most 963n, but again, x is just an n-digit number, so we get the same sort of lower bound that we had before. X is at most 10 to the n minus 1. Okay, so we have these two inequalities here must be satisfied for x to be equal to 107 d of x. Okay, and again, we can show, combining these two together, we can show that n must be at most 4. And again, to prove that, you can just use induction, or perhaps there's a quicker way to prove it. Basically, just note that this guy here grows exponentially, and this guy here grows like a linear term. So in terms of n, that is. So this guy here, there'll be some cutoff point, and then after that cutoff point, this guy here is going to grow way faster than this guy here. So there's no way that x can satisfy both those inequalities at the same time, and you just have to play about and find that cutoff point. But notice when n equals 5, for example, if you plug that in here, you're going to get something that's less than 5,000, which is certainly less than 10,000, which is 10 to the 4. So we can't have something being less than 5,000, but also being at least 10,000 at the same time. So that kind of tells us that n equals 5 is a suitable cutoff point. So we have that n is at most 4, and then what we need to do is just check the different cases. Because we know n is at most 4, and x is at most 963 times n, that tells us that x is at most 963 times 4. And because we know x is a multiple of 963, that tells us that x must be in 963 times 2, 963 times 3, and then 963 times 4. So if x satisfies this, then it must be one of these guys here. And then like we did in part 2, we just check each of these cases here, and we see that only one of them works, and that's the case k equals 1. So x would equal 963. Okay, and you'd have to check all the other cases as well and just plug that back into this guy here and show that the left hand side doesn't equal the right hand side. But if you look at the case where x equals 963, you actually get this equation to be true. And let's just quickly check that. If we have x equals 963, then what is the digit sum of x? Well, that is just 9 plus 6 plus 3, which is 18. So that tells us that the digit sum of the digit sum of x is just the digit sum of 18, which is 1 plus 8, which is 9. Okay, and so we get on the right hand side we have 107 times 9, which you know is 963, which is equal to the left hand side. Okay, so this is indeed a valid solution, and in fact the only solution, because when you test these cases here, which I'll leave as an exercise to you, you don't get the left hand side equals the right hand side. Okay, so that is the end of that step problem. I hope you have enjoyed it. I thought this was a really cool problem and really challenging, and not something which, you know, you could easily prepare for, but it's very classic in the style of step where the first parts aren't too difficult, or they shouldn't be too difficult once you have a think about them. But then the last part, when you just look at it, if I was just told to solve that there, that would take me hours upon hours upon hours to even have a idea of where to start. But you use the sort of, you know, the clues are kind of embedded within the solutions to the earlier parts. Using that, you can try and have a play about, and then using a similar recipe to what we did in part 1 and 2, we can actually solve part 3, which was sort of the main part of this problem. Anyway, thanks for watching. I'll catch you in the next one. Have a great day.